Hello, how are you? Everything is all right? Yeah, I'm fine too. Thanks for asking. Let's get started. So today's topic of the video is that do we understand Schrodinger equation and wave function? So in the previous video, we attempted to find out the wave function or Schrodinger equation from the classical mechanics. I explained you explicitly that how we are learning quantum mechanics. We are learning quantum mechanics from the transition from classical mechanics to quantum mechanics. We understood through this journey that classical mechanics is insufficient to explain the quantum phenomena and we have to change it. And I formulated this Schrodinger equation by some thought experiment that how we are doing some measurement. And we are going to follow only that description that, okay, we understand little bit of quantum phenomena, little bit of wave function, right? And but we have a very proper knowledge of classical mechanics. Therefore, I am a student of classical mechanics. I don't know many things about quantum mechanics, and but I am familiar with calculus, right? I am familiar with calculus, little bit of statistics, right? Statistics means that what? It just simply averaging mean that you have already learned in your class ninth, 10th, and maybe 11th and 12th, right? So little bit of calculus, statistics, and my initial topic was to reformulate the Newtonian mechanics with the help of action principle, and we have constructed the Lagrangian and Hamiltonian, and we formulated the Schrodinger equation in the Hamiltonian framework. So the Schrodinger equation, first I have to write it, is p square by 2m plus the potential. And this is the classical description of the Hamiltonian, but we found out that, as you are transitioning to quantum mechanics, this h, it simply become an operator, and this operator is going to act on the wave function psi, and it will then, I can write the whole thing as p square also become an operator, and the potential is also becoming an operator acting on the psi, right? Here psi is the wave function, and I show that the wave function could be the complex. And similarly, we found that, h can be written in terms of I h bar del by del t of psi is equal to minus h square by 2m psi plus v is an operator, that is potential, that depends on the spatial degrees of freedom and this wave function psi. And here the wave function is depending on spatial degrees of freedom, let us say x, y, z, and the time. So these are the explicit dependence, and right, for a moment now we are taking that, okay, psi is just a function of x, one spatial degrees of freedom, and there is some time, all right? And this wave function, I told you that this wave function is encoding all the information about the particle or quantum particle. So let's say that I have a particle in certain kind of dimensions. So let us say it is a box, and still I am interested in one dimension, that this wave function is one spatial degrees of freedom. I also explained you in the previous video that, there is no notion of coordinate system in when we are talking about the quantum mechanics, right? And we saw that this wave function is kind of n-dimensional, right? The quantum phenomena is not bound to occur in uh, in three-dimensional space, right? So here wave function, although depending on x, y, so what is the meaning when we are writing x, y, z, three spatial degrees of freedom? So why we are bounding? You see that we are bounding this wave function not to just, you if you think of that, okay, something is infinite dimension, right? Now, what is the meaning of infinite dimension? You think that infinite dimension from the classical mechanics is just x, y, z, maybe two more dimensions and so on. No, this is not what we are actually going to do in the quantum mechanics. Because, we are the classical object and we are interacting with the quantum system. And we know that the direction emerges in the classical regime, that what we are experiencing, that we can move from left to right and right to left, is because of the structure that emerges from the array of atoms, molecules, and so on, and then the structure emerges. But as we go deeper and deeper, there is no some structure. And we say that, and we also said that, there is no concept of trajectory exist, because we don't have anything related to coordinate system and so on. So when we are trying to interact, we are living in three special degrees of freedom and one time, or in the general relativity, we already understand that we are in four-dimensional space, but restricted to this one, that we have three special degrees of freedom and one time additional parameter we have, right? So we try to formulate a mathematical object, this psi, that have some degrees of freedom in the spatial case, and there is a spatial dependence of time, right? But the thing is that this psi could be n-dimensional, because what psi contains, as I explained you, that psi is containing the information of the particle that we don't know. I told you that if we put an electron on a subspace, right? There's a box. Let us say it's a one-dimensional box. I know the electron is here, but what is the energy? What's the position? What's the momentum? Because this is what we observe from classical mechanics, right? Now you may also ask that, how do we actually know what is the position, what is the energy? Uh, because you have to throw a light to this particle, and then light will come to it, and you will analyze that, okay, what's basically going on, what about the position, momentum, and so on. And I told you that the moment when you try to measure it by throwing some light, because these are quantum and light is also becoming a quantum phenomenon, they will going to interact and they are going to disturb the system. It gives you it pollutes the system. The more the energetic beam you are going to throw, the more pollution you are actually doing this quantum system. And because of this measurement and because of this pollution that you have created to this quantum system, you are no longer able to say that, yeah, exactly where it was before, isn't it? For classical particle, it is good, because if I'm throwing the light, it's not going to disturb anything, isn't it? If a ball is there, it's going to be there. If ball has some velocity, it's going to be there. Either I am looking at it or not, I'm pretty sure that, okay, nothing can, it's not disturbing. But over here, it disturbs. So if I'm not measuring, I don't know what are the configurations it have. Therefore, this psi, the wave function that I am writing, it's actually telling you that, okay, there could be many configurations in which the particle could be. And this is basically the famous Schrodinger cat problem. That, okay, let us say I put a cat in the box, and there is some radioactive material, and there is somehow it can, the radioactive material can release, and something like, something cat has done to radioactive material, and it may release or it may not release. How do I know? So if a cat is inside the box, I'm not doing any measurement. I cannot even say that either cat is dead or alive. If I will look into the object, into the box, then I will know that whether the cat is alive or not, or dead, right? And this is the very thing. So what you can simply say that, okay, there is a chance, if I don't know anything about the alive or dead of state of the cat, I can simply say that, okay, my ignorance, my intelligence get limited to this. Therefore, I have to take into account everything what is possibly can happen to this cat. So cat can either be dead and either be alive. And this is, people are inferring that this is a superposition state, but it's just nothing. It's the mathematical ignorance that you are actually doing. And it becomes, too much fundamental for quantum mechanics, that there could be many configurations of this quantum particle, and you don't know what are the configurations, and you say that, each and every configuration has to be unique. And when these configurations are extremely unique, then what you actually do is that you can write that, okay, I am going to take all the configurations over here, like psi1 plus psi2 plus psi3 and psi4. Therefore, what you basically do is that over here, psi of xt, therefore these are also becoming psi of xt, psi2 of xt, psi3 of xt. At the moment t is there, means that unlike the classical particle, right? Unlike the classical particle, let's say that if I have a ball in the box, the ball could be in one, state. Either it is in velocity or it is in rest. I know perfectly. So at the moment, I know that the classical object has only one state. On the other hand, if I'm not doing any measurement at any time, or at, let us say, t is equal to 1 second, it can have many configurations because I don't know about those configurations. Therefore, I have to take into account everything. And this has now becoming the superposition principle. Now, why I'm calling it a superposition principle? It has a task. It has the origin. And the origin comes from, you have already done it in the classical mechanics. Let us say you have a region, and in region there are bunch of charged particles, right? Q1, Q2, Q3, Q4. And somebody has told you that, okay, could you find the electric field over here? And you say, yeah, indeed I can find the electric field. Just measure the distance from here, let us say R1, R2, R3, R4, D2, all the charges. And you see that this electric field would be written as E1 vector, E2 vector, E3 vector, and so on. And this becomes some kind of a constant. Q1 over R1 is square, KQ2 over R2 is square, and so on, right? And you will see that this is actually equal to the net electric field you are going to get over here. Now, classically, what we have done, there are charged particles, right? And we are considering charge as the classical thing, although it's not a classical thing. But the effect that we are actually understanding the classical one. So here we are saying that, there are a lot of charged particles are there. I can easily, write it as a linear combination of all the electric field due to different charges at different locations. And you can easily, you have already done, if the charged particles are huge, then I can write it as a summation. I will convert it into integral. Therefore this becomes dq over r square, 0 to, let us say, 0 to r, you want to find it out. And we have verified that this actually works, and this is the superposition or in the classical mechanics. This is true for any kind of forces, right? And because of this, the structure over here that we are studying called the superposition. But over here there is a different. Over here we have only one particle, and these particle at the same time can be in a different configurations, can have different configurations. And because of this, people are interpreted it as a many infinite worlds, alternate worlds, and so on. You have also heard of that. Okay, let's say that you have built a time machine, and at this moment you to choose a time machine, and you went to maybe in future, okay, and okay, maybe in past, and you have killed your uh, grandfather, okay, you have killed your grandfather. So when you have killed your grandfather, your father was never born, and therefore you were never born. But if you have never born, how you have arrived over here and killed your grandfather? And this is called a paradox. This is called a time paradox, that if you will, do the time traveling, lot of catastrophe can happen. And therefore, in nature till now we have seen that there is no time travel occurs, right? Now here comes the superposition principle, and people try to save it by saying that, when you try to jump through time, you are actually trying to go in back in time, but a lot of quantum things can happen. So the moment when you time travel, let's say that you have time travel 50 years before, but at this time you see that for each and every particle there could have many configurations, and the probability of landing yourself into the exact same configuration is negligible. So you are going to see the same world, but it has many different copies. So the moment when you have killed your grandfather, you have actually not, let us say that you are from this wave function, but you may have this wave function, this wave function. So if you have not jumped to any of, if you have not taken a time travel, then all the copies are going to be same. But the moment when you are time traveled, you have created a different copy. And you have also seen this seen this branch kind of thing or time travel thing in maybe the Loki series, right? So this is a thing that, okay, the moment you have killed your grandfather, you have, influenced thing, or you have taken the journey to the past, you are landing on one of the different wave function. So now you have actually created one of the timeline which is different from others. And when you are coming back, you are actually coming back to your journey, not this timeline. All right. So this is what happens is that, the quantum mechanically, although you can change the past, but whatever your present is not going to be influenced, because you have now created many different copies, and one of the copies has different structure, because now you have interacted it. The moment you have interacted it, you have changed the world. All right. And maybe that's why we are not able to go back in time, because the somehow the nature prevents us that, you cannot just make a different copies of universe, but it can be possible, right? So these are the concept that is actually associated with the superposition principle, that, indeed there are, because experimentally we have seen that this is possible, because, the wave function can have different copies. It's the mathematical concept, but experimentally it is now verified that, yeah, quantum wave function is following the superposition principle, because of this, we have up all the experiments. So from the back calculation you can say that, okay, because it everything has emerges from here, therefore you can say that, okay, this is true, right? But now there is one important thing that I want to discuss. So this is what the superposition principle looks like. That, okay, this is the superposition principle. But mathematically, these are all mathematical concept, right? This psi 1, psi 2, psi 4, psi 5. So let's say, as I told you, that I don't know anything about the experiment. Then who told us? I told you that, we don't have any information regarding the electron. But who has told us that, you have to just simply linearly add those psi 1, psi 2, psi 4? Can't I just, because there is no any fundamental thing, nobody will stop you that psi is equal to psi 1 square. You can just simply add it now. Psi 1 square, psi 2 square, psi 3 square. Just add it. Who has told you not to do? Or you may just say that, one of the configuration can be linear and other configurations could be non-linear. Let's say this one. Psi 5 square. Maybe there is some kind of a cube going on. Psi 6. So on. There could be many configurations. Who told you that there always be only linear? Maybe you see that there could be some non-linear effect in this superposition state. But since we are actually, in our experiment, we are not probed too much, therefore we are actually seeing the effect of linear, but we are seeing not effect from non-linear. Maybe in later, or maybe 50 years later, we will understand that, superposition principle has some limitations, but we can also take these things into account. So research is going on, but let me just tell you that why we have expanded linearly: psi 1, psi 2, psi 3. All right. But let me just again get back to the classical mechanics, as I'm very used to go to classical mechanics, right? Now, a very interesting thing is that, when I wrote that electric field can be written as E1, E2, E3, and so on and so forth. And from the electric field, we have a very known calculation that electric field is the gradient of the potential. Since whenever you have a field exists, there would be always a potential. And potential is a scalar quantity, and also this scalar function is following the superposition principle that, okay, whatever the charge, you can just simply add it, right? Now, why we can do this? First of all, let me just give you that why I can just do it. All things mathematically. You see that if I replace this phi 1 like this over here, what will I get? I will get that this thing will, you know, uh, operate, because this is in one dimension becomes del by del x. So it's simply d by dx phi 1, d by dx phi 2, d by dx phi 3. And we know that d by dx is proportional to electric field. This becomes what? E1, E2, and E3. Why I'm writing plus? Because this is defined as negative of this one. Negative of this one becomes E1. You see that I'm getting back the superposition principle, right? Now you have to understand this is a linear operator. Okay, this is not a non-linear operator. So whenever you encounter differential or the integral, these are called linear operators because you can always, these are also called, sets. So if you let us say any set and you take any function and you will get the output, the range, and still you are going to get this f inverse and you are going to get this same thing. So if this is following this, you can simply say that okay, these are the one of the properties of the linear operator. And hence, since d by dx is a linear operator, therefore it is better to it will act on it and you are going to get these things. Therefore phi 1, phi 2, phi 3, these are the potentials I'm talking about. Phi 1, phi 2, phi 3 are expanded linearly. On the other hand, we also know the Gauss law. The Gauss law implies that if you take the divergence of electric field, it is proportional to rho by epsilon naught. And I have now seen that electric field is negative of del phi is rho by epsilon naught. So it simply becomes del square phi is negative of rho by epsilon naught. And I told you that this is phi 1, phi 2, phi 3. And again, if I am just expanded it in terms of phi 1 plus phi 2 plus phi 3 and so on, the right hand side is not going to change. This is the total energy density. It simply says that you can write the energy density is from, let us say, rho 1, rho 2, rho 3 and rho 4. If you have any compartment, all the charges are there. This actually told you that this is the rho total. The total energy density of that compartment is equivalent to this one. So when I'm applying this guy, it has again the same thing, linear effect, del square phi 1 plus del square phi 2 plus del square phi 3 and so on is proportional to rho by epsilon naught. So right hand side is not going to change, doesn't it? But suppose that the phi is not proportional to phi 1, phi 2, but let us say it is phi 1 square and many more things, then what will happen? You see the first change you will encounter over here. You don't have to go further. You can simply see over here that okay, electric field would become minus of delta phi 1, it is good, but this would become simply minus of 2 phi 2 delta phi 2. Now this guy would become E1, but what about this guy? This guy becomes 2 phi E2. It is not giving you the superposition state of electric field. This is not true. Experimentally, we have the validity of, in classical mechanics, we have the validity. So if I see the nonlinear effect, there is additional 2 phi 2, and over here I can write delta phi 2 as the E2 minus delta phi 2 as the E2, but there is phi 2. Why it is there? Therefore, electric field is no longer is E1 plus E2 or E3 or maybe E2 square. No, it has changed, right? And you are not going to get the solution. So this is the reason why we have chosen that okay, either we don't know anything about the configuration of electron, right? Therefore we take our ignorance and write it linearly, psi 1 plus psi 2 plus psi 3, and later on we have interpreted okay, this is basically the many world scenario. You go back and kill your grandfather, but still you will exist because you are not landing on that timeline. You have created an alternate timeline, isn't it? So this is extremely great, and that's why the superposition principle works. And we have not seen any effect on the nonlinear scenario, but research is going on to understand that okay, what if we are going to add the nonlinear term in some way, let us say in a controlled way, somehow in some mathematically, can we simply write it? There is a way to write it, but right now I'm not going to expand it, but later on I'm going to discuss on those scenario too. So this is the thing. One more important that I have to discuss is that when we write the differential equations or the differential equation, the solution itself becomes a differential equation. Why? You see that in classical mechanics, I told you that x dot is becoming minus of x, correct? So this is the Hooke's law, that spring is attached to any kind of But this one, it will become it will give you the oscillating scenario, like x is equal to, sine omega of t and so on, right? So if I simply take dx by dt, it becomes cos omega t and omega. And if I take another derivative, it simply becomes omega a square sine omega t. Now, just simply put it over here, it becomes omega a square sine omega t. And if you just simply write over here, it becomes sine omega t with negative. Obviously, there would be omega a square, because this is omega square, k by m, omega a square. You see that both the side is satisfied, is equal. So whenever you encounter differential equation, the solution itself is a differential equation. Therefore, if I am writing x in terms of x1, x2, x3, x4, this solution will itself become a differential equation, right? So these are the whole mathematical concept. But now, when you read the quantum mechanics, you feel that, okay, where this has come from? These are all mathematical concepts. And we have given a layer of physics, layer of interpretation. That this is how you have to interpret it. Okay? So now you understood one thing? Okay. Now let's move on to some interesting and amazing thing. But let me just tell you one more important thing, that when I'm expanding this psi in terms of psi 1, psi 2, psi 3, I told you that this is kind of a vector, because vectors are also adding up like this. Because let us say that if you have any vector, you can expand it in terms of a2x, y, and a3z. And I told you that this x, y, and z are the orthogonal component, because if I'm writing this as 1, 0, 0, a2, 0, 1, 0, plus a3, 0, 0, 1, right? So you simply see that whatever in x, it's already there in a2 and a3. They are completely, you can always say that, okay, I want to only see in what happens in x. You can easily see it, right? So these are linearly added. Therefore, these are also linearly added. So I can use an abstract concept of vector space, which I'm not going to cover over here, but in the next video, I'm going to talk about the vector space. And this will become a Hilbert space of infinite dimension. And this dimension comes from the configuration of this psi 1 and psi 2, that how many configurations is possible. It can have infinite configurations. And vectorially we are adding it. And these psi 1 and psi 2 have an interesting relationship, that they are orthogonal. You can say that orthogonal means that psi 1 is perpendicular to psi 2, but not in terms of dimension. You can say they are not dimensionally perpendicular. What I meant is that these have unique configurations. And if you take a dot product, the way we are defining it over here, you take a dot product and they are going to be 0. And you have already seen that in vector, if you have two vectors, you have taken the two vectors, you take a dot product, they are going to be perpendicular, because cos theta, AB cos theta, theta becomes 90 degree, it's going to be 0. And if two vectors are orthogonal, means that the angle, two vectors having the angle 90 degree, they becomes orthogonal. That is the meaning over here. So in the later video, I'm going to talk about the Hilbert space, why it is its infinite dimension, you understood, and what kind of algebra it can have. But obviously, we can say that this is a column vector. As I told you that this A vector would become what? A1, A2, A3, this column vector. Similarly, psi infinite dimension, I can write as psi 1, psi 2, psi 3, psi 4, and so on. Right? It's a column vector. Now, a very interesting thing. Okay, when I'm writing this psi, his whole column vector, therefore, when I'm operating over here, let us say I h bar del by del t psi, right? This is basically s psi. S now is an operator. Operator means that any function that is going to operate on something and will yield something, right? For instance, sine is an also operator that is going to act on angle. Depending on the value of angle, it will give you some value, right? That's why we are calling it h as an operator. It's not just h, it's an operator. And I told you that h has to act on the state and then it will give you some value. But for instance, for now, what I'm going to see is that, I h bar del by del t is psi. This is an operator act on psi. But psi is what? It's a column vector. It's a column vector. that encodes all the information about the electron. Therefore, I have to write I h bar del by del t for each and everything, psi 2 and so on. Later on, we are going to see that, whatever we have done, we can also, it has the representation of the matrix. Right now, we say that all everything you encapsulate right over here. So if I want to write, I can easily write I s bar d psi dc. So what is my Schrodinger equation? The Schrodinger equation is I h bar, if I'm writing everything correctly, del by del t psi is equal to minus h square by 2m del 2 over del x square plus v of psi. Now, not v of psi, v acting on psi. If I want to write it in terms of vector, I'm going to write it d by dt, I'm writing psi dt of psi 2, so on, minus h square by 2m, these are constant, therefore I'm just taking outside, del x square psi 1, del x square psi 2. Similarly, v acting on all these psi's, psi 1, psi 2, psi 3. So later on, we will bring the matrix concept over here. So these are called family of differential equation. Family of differential equation, which has to be solved simultaneously. So when you are seeing over here, many times when we were learning, we are saying that we thought that, why we are actually doing some matrix computation, because, we are coming from the background, class 12 background, where we have done this thing, del f by del x, or, f could be like sine x, sine theta, sine x, cos x, all these things. There we have not seen anything like this. And momentarily, when you are hitting quantum mechanics, when you're learning quantum mechanics, there are a lot of, mixed concept coming from, mixed concept, right? And because of these mixtures, we are very confused that sometimes you do matrix, sometimes you do, derivatives. For us, it was familiar, right? You have also feel that this is very familiar. But when somebody says that, psi 1, psi 2, why you're writing psi 1, psi 2? If we have if we have little bit understanding, but it's not clear. But now it is very much clear that why we are writing it. Isn't it? These are called family or differential equation, and you have to solve for each and every row. And then when you are accumulating, you are going to actually get this one. And that is the beauty, that everything becomes a linear. Isn't it? So this thing you have to understand that, we can talk about matrix in this quantum mechanics, right? And one more interesting thing, I must tell you that in this equation, what is unknown? The unknown is that we know what are the operators. The unknown is the wave function. I have to know, because this wave function has to be satisfy this differential equation. Then I will know that, okay, these are the configurations that this electron that I put in the box can have. But now, and this equation is also called the eigenvalue equation. It's a mathematical concept. So just I am, before I'm doing anything, I'm just simply tell you this, why it is eigenvalue. When I'm writing h, it has to operate on psi. What is the output? You will say that why not? I am accustomed to write this thing. But I told you that, h is what? H is Hamiltonian, and h is proportional to what? Energy. We have already learned that h will eventually give you energy. So let's say that if I have a closed system, electron is putting there, nobody is disturbing, no energy is flowing. So this energy is going to be independent and give you the energy of the system. Therefore, this h when act on the psi will give you energy and the state psi. Right? Whatever the state, because you see that if I'm talking about classically or quantum mechanically, right? The energy is only thing You can just blindly say that obviously there would have some energy. I don't know anything about momentum and position, but energy is something there. It should be there, right? So all the possible, configurations you may take, energy would be there. I don't know what is the energy of those levels, but you can simply say that, okay, energy would be there, right? So now you see what is not known. Over here, the wave function is not known, and what are the energy of the electron? That is I put in the box. Therefore, it's too much important to actually figure out what is the wave function or what, and for what value of E this wave function is going to satisfy. And therefore, because German scientists were there actually to who has discovered the so-called general relativity and quantum mechanics. Therefore, this has now become eigen means that its own, or you may say that self. So it wants to know that for what value, for what function of H is going to produce E. So this is kind of constraint equation for this one. Constraint equation. Where psi, the solution, psi must exist in such a way that it satisfies this equation. And still, the energy is unknown and psi is unknown. Right? So this energy is now becoming your eigenvalue. That if I have acted H on psi, it will produce the eigenvalue. And this eigenvalue has to be real because we are talking about the energy, and energy cannot be negative, so energy has to be real and positive. Okay, and I still don't know what is this psi, and these are called eigenvectors. And why I'm calling it vector? Because of this property. Eigen means that own value. What is this own value? What is its own vector? These two are unknown, and hence this equation is actually there as a constraint equation that is going to give you the glimpse of what would be its own energy and own eigenvalue. So let's say that I have isolated my system. There is no interaction out there. There is no time dependent function. Therefore, H will act on the psi. It will give you the eigenvalue. E has to be real. I will act on this one. I H bar del by del T psi is equal to E psi. I have ignored everything. You see that this psi is a function of X and T. Psi is a function of X and T. And when we are talking about the partial, when you're talking about the wave function that is depending on two variables and there is a partial derivative, I can always write it xt as, let's say, some function of x and some function of time t, right? So this becomes, if I take a time derivative over here, this is become constant and the time derivative will occur over here. So the equation would become, right, del t over del t is equal to E x and t. X get cancelled out. You see that now you have only t dependence. So I h bar del t by t, you know how to solve it, E over I h bar, and this becomes log t by, let's say, some constant t naught, E over I h bar t. Hence t would become, if it will go, exponential E over I h bar t, and this becomes t naught. It says that if I'm just writing, how it simply says that how the states will evolve with time. So if I'm writing psi would become some function that depends on spatial degrees of freedom. I'm absorbing this thing into this one, and it will simply tell you I e over h by t. So how these states are evolving with time. So once you have formulated what is your psi xt, it's telling you that okay, with time you don't have to do much experiment. It simply tell you that okay, what would be its, how the time will happen. So for different for energy, for a specific energy, it simply tell you that what would be the wave function at later time and so on and so forth, right? And this is becoming exponential. You don't have to worry about, because I told you that from this one you can understand the simple calculation tells you that this psi is a very complex function, and there is a way to find out the real thing. I told you that the probability from the Born thing would become psi square, but this psi square is not this psi square but the modulus of psi square. This modulus of psi square is basically psi star psi. Psi star is called complex conjugate of this thing and psi. So you momentarily see that this x becomes square. I don't know what is, so I have to write it because x could be also complex. These are wave function. And e to the power it, if you take a complex, you will get I becomes plus I, e over h bar into t, and this is minus I e h bar t, right? Psi star and psi plus I minus I. If you just add it, because bases are the same, you're going to add it, it's going to be 0. E to the power 0 becomes 1. It's proportional to x square. So what's important over here? The important is this finding that how the wave function is spatially going to vary. So if you have taken any kind of system whose energy is not going to change, let's say it's isolated, you don't have to worry about it, what happens in the time. You have to worry that how the spatial degrees of freedom would behave. Because no matter what, I'm interested in probability and the complex conjugate. I have to take always this complex conjugate in order to get a real value. And this complex conjugate has meaning. We call it as adjoint. In quantum mechanics, you will see this star is replaced by psi is called dagger. This has meaning. The cross is called dagger, right? So this dagger, both have the same meaning. So if I write e to the power it star minus it, the same thing will happen, e to the power it dagger, e to the power minus it. So do not confuse, because we had the confusion that okay, sometimes you say that complex conjugate, Hermitian dagger, and so on and so forth, blah blah. It's a very simple thing. It's a complex, make to real, you have to multiply with this psi star, all the mathematical concept. Don't have to worry about it, right? So that's why I'm telling you that the feeling of naturalness must be there when you actually teach, or when you are learning, that you are not learning anything new. So I'm talking about what? I'm talking about these important things, that how the matrix will emerge, matrix emerges, and as well as we have to deal with a lot of matrix thing because of these properties. And if we are taking the isolated system, these are the things that is going to happen, right? Now, there are many things I have to discuss in this video, so therefore you have to keep some patience. One more interesting thing I have to say, I told you that this is called, when I'm writing h acting on psi, will yield you e of psi, right? And this is called eigenvalue problem. Eigenvalue problem. And you see that this h is kind of complex, but this energy has to be real. Eigenvalue is kind of yielding, right? That okay, this is the value that I am going to see if I am doing the experiment. I cannot observe any complex because your instrument has not designed to measure which is not there. Complex numbers are a mathematical concept, right? You're not going to see there. Although this mathematical concept of complex number arises when you do deal with AC, because we are writing the phase in terms of complex numbers. So mathematically, these complex numbers are very easy to description. But in reality, what we are actually interested in the amplitude, right? Not the phases. But again, the phases are important because if you want to do some thing, but what actually you are doing, you are observing, is the real thing, and complex thing will actually help. Now, what is this thing? You are actually expecting that your operator, when act on the wave function, must yield a real value, right? This has to be real, no matter which, no matter what. And this is also a linear operator. I see. Why linear? Because it is a differential equation, right? It's become a linear operator. So you have also heard that okay, has to be linear. Why linear? It's a differential equation, right? Very good. Now I told you that if I do the measurement once, I cannot rely on the value. So here you see that h operate on psi will give you e and psi, and this becomes an eigenvalue problem. And you have also maybe seen in the matrix, you will see that I told you that this is also a matrix equation. Therefore what you see that h bar psi minus e psi is equal to 0. Hence, h bar minus e when act on psi is equal to 0. So e will become a eigenvalue. And if I just give you an example, let's say that okay, there is a matrix a11, a12, a21, a23. How you can solve it? Minus, let us say that some lambda is eigenvalue, and therefore you have to multiply by some identity matrix is equal to 0. How is visible to you? Right. Now, this would become simply a11 minus lambda, a12 would be there, a21, a23 minus lambda. You see, then you have to take a determinant of this. This becomes a11, a23 minus a11 lambda minus lambda a23, and then there is lambda square, a12, a21 is equal to 0. Now you see that when we have taken the lambda, depending on the dimension of this one, lambda has second order, this become a second order polynomial equation. How many solutions you expect? Then lambda would have two real solutions. It has to. Because my demand is that lambda is real. It has to be real. The eigenvalue has to be real, isn't it? The E has to be real. So if I am taking some kind of a matrix over here, then this lambda has to be in such a way that it should yield a real value. Now, if I know what is this lambda, then again I will put back over here. Let us say that this is your A, and let us say psi becomes a lambda psi. Then I will say that okay, A is A11, A12, A21, A22. Psi could be psi1, psi2 is equal to lambda. Let's say I will solve for lambda 1, psi1, psi2, and then similarly I will solve for lambda 1, and then I will solve for lambda 2, and you will see that you will get the two eigenvectors. So you will see that there are, because this is known, because this is called the H, right? The operator I know. The unknowns are psi1, psi2. So for each lambda, you are going to two unknowns, two equations, right? So should I write it? Okay. If I writing, I'm going to multiply rho by this guy, lambda psi1, a21 psi1, a22 psi2 is equal to lambda 1, lambda 1, a1, a2, these are knowns, psi1, psi2 unknowns, two unknowns, two equation I can easily solve. Similarly, for lambda 2 would be different, and that's how we are going to get these eigenvectors. So that is why these are called the eigenvalue problems. H minus E psi. But the question is that, these are the linear operators, agreed. You say that E has to be real, agreed. But how can I make sure that E will always be real? Because this is a complex equation. Well, there is a very mathematical property you can see. I am saying that H operate on E becomes E psi, right? And I know that psi star psi will going to give you the probability. If I take the integral, probability of from minus infinity to infinity is going to be 1, right? This is the proportional to the probability, or also called the normalization constant. So what I should do is take a conjugate, H of psi, E of psi. I told you that E belongs to real number. That is my initial statement. Now you see over here that I have to find E. Now it's coming with psi. How can I find only E? I say that okay, I have to take an average, because when I do the measurement, I'm going to do the measurement several times. So what is my interesting thing? My interesting thing, the value I'm going to get after averaging. I am not relying on only one thing, only one value, right? So therefore I'm going to multiply H psi is psi star E psi, and I'm going to take over the averaging, take over this one dx, right? You see that this is an operator, and when I do this, this is basically average of the observable, because this is going to give you lend you the number, and E is already a number. Bring out from this one, psi star psi becomes 1. So this becomes 1. You see that this average value is just a number, E, right? This is what we are actually interested in, E, right? Now, if I do the same thing over here, first of all, let me just write it. What will I get? I will get, okay, H, writing a star, psi star is equal to E is a real number, conjugate of real number is just E, and this becomes psi star. Now, what will I just do? I am going to multiply psi H star psi star is equal to E psi star, taking the integral dx. What is going to become is either I'm writing this one or maybe this one. This guy is always going to be same. Now, two equations right hand side are equal implies that, this H is going to be H star. It simply says that, this operator that you are talking about, the complex, it may be complex or anything. Obviously, it's a linear operator. Then it must be equal to its complex conjugate. Either you write this way or write this way. If this condition satisfied, it is guaranteed that whatever you will get the output is going to be real, right? And this is what we call the Hermitian operator. It has the name called Hermitian operator. Now I'm talking that I'm not a student, I have to teach, right? So therefore I have to give you some the name and so on. If you will look at the book and you will see that, very different things, because I'm very bad at remembering those names. But I follow that, okay, this is called Hermitian, so this has to be Hermitian, right? So this has now becoming a Hermitian operator, right? So this is very cool. There, if I just required my eigenvalue, do the averaging, take some complex conjugate, you know how the complex analysis actually works, and you will see that, the H has become the H dagger or H star, and it just gave me the glimpse that, okay, this has to be there. Now, you may say that, okay, fine, if it's H, you have not done anything. Let's say that, okay, momentum is operator acting on this one, let us say give you the eigenvalue psi. Great. Now, okay, then what will you do? How will you find that, okay, momentum is Hermitian or not? Well, I'm going to again take the same route, because these are linear operators. That's why you can, always follow these types of route. No problem. Integral, dx, either you want to write or not. This is lambda, right? But let me just hold right over here. This is lambda, right? Okay. I'm not writing this guy. You will say that, you can auto cheat. Let me just use this guy over here, I h bar. This is my definition, because yet in the book you will see that momentum has minus I h bar d by dx. But we have derived in the previous scenario that p becomes I h bar. We will fix negative sign, but not now. We will do later on, because we have not yet gone to complete quantum. Oh, we are doing quantum, but not in the sense that we are doing actually the calculations of quantum mechanics, right? Of real problems, for instance, the hydrogen atom. Okay. So now you see, very interesting thing, that, okay, I h bar d by dx acting on psi is going to be lambda, right? Now, what else I can do? I say that, this lambda is going to be real. Taking the lambda star will also give you real. And this, and again, I'm going to take one more step. I h bar, wait a second. Should I write this one? D by dh. No skipping of steps, right? It's valid. Now, when you do this, psi star psi would become psi. I would become minus of I h bar. H bar is just a constant. D by dx, I don't know what. Let me just say that, okay, this is the thing you are going to get, psi star dx. Right. Now, this becomes I h bar psi. This guy will operate on this. Now I will do the thing. You see, if I just take d by dx of psi star, then what will I get? I will get that, okay, d will operate on psi star would be there, plus psi star would be here, d psi by dx. right? I'm not doing it. Just remember, it's a simple case of um, how we do the derivatives, right? So I can write it like, what's our thing? I have this, right? Okay, d psi by d psi star. Then it has to be star, and this is non-star. So I have this guy. I can express this thing like this. So I will write d by dx psi star minus d psi by dx, and maybe this you can write over here psi star, whatever you can write, no problem, dx. Now psi star becomes what? Some real thing, and it's not going to vary. D by dx is going to be 0, minus minus plus I h bar psi star d by dx psi dx. This is actually becoming lambda, and psi star, this is I h bar del by del x psi dx. And what is this? This is just a momentum operator, right? It tells you that, you see, if I just take a complex conjugate of this momenta, it is going to be real. So how we have done? I first defined this p acting on psi, some lambda, this guy over here, taking the complex conjugate, and I have changed everything. And I arrived that, either you have taken this complex conjugate, is going to be Hermitian. And a very interesting thing you are going to see over here. Let's say that, forget a moment of that P is equal to I h bar, right? If I just say that, I h bar could be replaced by some alpha, right? Let's say it's alpha, and alpha is a real number, correct? Some alpha. Alpha, let's say, is a real number. So this becomes alpha. Alpha star is alpha. Alpha star is alpha, some real number. This is alpha. This is alpha. Isn't it? Okay, wait. This becomes 0. This becomes minus alpha. And now this will become minus of alpha. You see, you are going to not get minus of p. So p star will give you minus of p. That implies that if you have del by del x and you will take the complex conjugate of this one, eventually you will get minus of dx. So the thing is that if you have p proportional to del by del x, doing the complex conjugate will yield not d by dx but minus of dx. And this type of question could be asked that, show that d by dx is equal to minus of dx. How you can show? It's simply taking that I h replaced by alpha. Alpha is a real number, and you will eventually see that this is not going to fall this one. So you can say that d by dx of dagger or Hermitian conjugate is actually produce you minus d by dx. And this is not same, this is our anti-Hermitian. So d by dx is called anti-Hermitian. Anti-Hermitian means that not same, it will pick some negative sign. And this is the way you can, easily show it. Therefore, it is important that your momentum becomes complex. The momentum operator has to be complex. And, in quantum mechanics, you will see many things that whatever the operator in general, it will come out to be complex, so that the eigenvalue has to be, real no matter what. So this is how, I have not taken anything, any concept of cat and browse and so on, and I have also shown that using just only differential equation, because we are coming from class 12, not throwing something to you, right? Now, another thing that I would like to discuss is that, well, we have talked about the wave function, we have talked about the operators, that these operators has to be do. But one important thing before I'm going to, some interesting feature is that SI will tell you E psi, right? So let's say I have some operator or some matrix whose, let's say that if I take the inverse of this one, I will get inverse and its matrix, all right, or maybe operator. You will get u inverse in u is equal to identity. It's not going to change anything. Psi is equal to u inverse u of psi, right? Okay, I don't have to even write it. U inverse u is equal to e psi, right? Because it's completely this one. Now I am just multiplying this u H U inverse U psi is E U of psi, right? No problem. Left hand side and right hand side are equal. You see that this now becomes something interesting. This we can write as a H tilde. H tilde operate on U psi is giving you the eigenvalue, this one. You see that the state is now becoming U psi, but the eigenvalue is not going to change. So if I have any Hermitian operator, right? Any Hermitian operator, and if you do some kind of transformation with some matrix, if U and U minus U inverse, will give you the new type of operator, but whose eigenvalue is not going to be changed. This is called the transformation of operator, and this transformation can be done by something called a unitary operator. So if you will replace U inverse by U of complex conjugate, or maybe U inverse by U of dagger, you will realize that U dagger U is equal to identity matrix or identity operator, where there will identity operator means that IL 0 0 0 1 0 0 0 1. So this is have only diagonal element. That is the meaning of. So it's not going to affect your matrix or operator in any way, right? So if I just do something U dagger, I'm going to again get a new Hermitian operator. Everything has to be linear, but the eigenvalue is not going to change. And that is very interesting. Because now when you do the transformation, we have shown that maybe in Lagrangian that we have changed the position by something, and let's say that the Lagrangian is going to remain same. We have some kind of a symmetry, that we have corresponding symmetry, right? And similarly, the similar thing happens over here, that here we are not changing the coordinates, not changing the special degrees of freedom. That will I'm going to talk about. That is the kind of a research thing that I will talk about later on. But a very simple change I can do with the operators over here, that if I have some specific kind of transformation that follows this unitary operator, where U dagger or U inverse is equal to U of this dagger or U of complex conjugate, then the operator is going to be transformed into H tilde in such a way that your eigenvalue is not going to change. That is what we want, that the eigenvalue should not change. If it is changed, the game is over. It should not change, right? So it has the symmetry, right? Some kind of symmetry that it's not going to change. What is not going to change? The E is not going to change. And then we are going to see some evolution of time, that okay, what we are, if I just take the Hamiltonian any operator, if I'm going to get a time derivative, then what is going to influence, what is going to see, what is we are going to get. That is the topic of not this video, but the upcoming video. But we have talked about very interesting things, and we have talked about various key things. But one thing I must address is that, you see, when I do some measurement, it perturbs the system. It is not going to give me the whole information. Some of the information is we say that we don't know it, right? But the problem is that how much information we don't know. Can I ever not able to get that information? So basically in physics, what we do, we have talked about, that okay, this is the thing you are going to get. But in physics, or if you have ever gone to laboratory, you have, let us say you have a meter scale, and you try to measure the length of some object. Let us say it's start from 0.1 centimeter, 0.2 centimeter, and let us say it become 1, and so on. So if I am giving you a pin whose thickness is 0.1 centimeter, so you say that okay, this is a 0.1 centimeter. But if the pin is extremely small, then this one, let's say your hair, so hair will fall between 0 to 0.1. What would be your result? I don't know, right? Or maybe let us say that you have measured something. Least what you can measure from this meter scale is 0.1 centimeters. So if I give you any pencil and I'm saying that, okay, give me the length, let's say that you say that, okay, the length is L0, but you will say that no, this L0 have some kind of, problem, because no matter how, whatever we are inventing, it would be some error. The error is plus minus 0 centimeter. So maybe it is little bit lesser than 0.1 centimeter and maybe a little bit greater than 0.1 centimeter. And this is we call accurately, how accurate you can measure. And the accuracy of this mean value, that is called the mean value that you are actually going to get. The the accuracy of this value is depending on that what is the accuracy of your measurement, right? How accurate your measurement is. And the accuracy will be determined from this one. So if I'm writing the length of anything, it would be the value, the true value, and the error that is coming to this value. So if you have seen any kind of experimental book, paper, they are going to write, let us say it is 5. So 5 plus 0.2 plus minus 0.2 centimeter, this is called the error. And because of this error, I am saying that, okay, that is the sensitivity of that instrument or the validity of the result and so on. And that is the thing that you have already heard that, okay, you have to go more and more accurate. The more and more accurate means that, okay, how much you can go further. 0.003 centimeters, 0.00003, this one. This is actually tell you that the accuracy that you can have. So in quantum mechanics, when we say that if I do measurement, the measurement can pollute the system, therefore the result that I'm going to get has some error. But the question is that what would be the error? Can I even estimate the error? Is there any way we can say that, okay, this could be the error? Are you understanding a point? So let us say that if I put the electron in the box, I am hitting from with the light, have some wavelength, it will again come back and it will tell us that because when you are hitting it with the light, let's say that the light has lesser energy, it is not going to give you any kind of much energy, but momentarily you are going to hit, it will give you another state because it will take, right? It will influence it. So the position will change as well as momentum is going to change. Now we are saying that the energy is not going to change because we have not supplied too much energy. Let's say energy, whatever the energy is there, it's going to be great. So let's say that if I am acting my x on the wave function, it will have the new state phi x. But the question is that, okay, how accurately we are going to measure. So let's say now from the classical point of view, let us say that we are doing the data, we are doing some experiment, and I have to report that, okay, what would be the length of several things. I'm not going to just measure once and I will say that, okay, this is the thing, but I'm going to get the measurement for 2, 3, 4, maybe 20 times, 30 times, and so on. And I will see that, maybe something 0.2, 0.21, sometimes 0.19, and so on. This is going to get. So these are the data points. And again, I will write the error, corresponding error. The error is going to be estimated. What is the complete error and what is the average thing and so on. What would be the average? I'm going to write it using the standard deviation. This standard deviation is actually with the data point from the statistics is defined as, let us say, all data points considering to be data. Take the square of this data, whole data square, minus the average of the data and then a square. And this is give you the uncertainty. You don't know anything about it. The uncertainty in the data. If the uncertainty becomes greater, we cannot say that this data is significant one, right? This is the act of measuring, right? So if you will see the cosmology paper or any other papers, they are going to give you the uncertainty, that what is the uncertain, the error bars is going to be very high, very huge. I'm not saying that, okay, this data points is very accurate, and you have seen that these data points are actually like this. These are the error bars that are going to show, right? So standard deviation is going to give you the uncertainty in the data. And similar thing we should must get over here. The data is square, then you are going to average. First you square the data, average it, then you have just say that okay, I'm taking the average and then squared it. What would be the result? Right? So it's the deviation you are going to seek. So first of all, I am going to define that if I have delta x, and the definition goes like this: x minus, let's say, its average value. Okay, how far it is going to get. Now this is an operator, and I told you that when you are writing the expectation value or the average of this, I'm saying expectation value, when you are doing the average of x, you are going to get a number. So you may just say that okay, whatever the output is going to just a number. So this x, when operated on psi, is going to give you like this. Operate on psi will produce you some new state because it's going to change it, right? So we have delta x bar, x hat is equal to x hat minus this one. Let's say I'll take it, I'm going to define that okay, whatever the square that you are going to do with this thing is going to be the uncertainty corresponding to this measurement. That is sigma x. Maybe sometimes people write it as a square and so on. Sigma x square would become what? It's simply become x square minus of delta x square, sorry, plus of delta x square. This becomes 2x and delta, and this one x, right? Now the question is that, when we are taking the value, the quantity that is we are interested in the average value. So sigma x, we say that there are some kind of uncertainty. What is the expectation value? What is the average of this one? So I'm going to write the average, and average is denoted like this: x square will be x square, x square. This becomes simply a number, so no problem. But this becomes x and x. That's I'm just taking the average, right? The definition of this one is just simple like this: psi star sigma x psi with squared dx. That is the average, right? So if I just simply invoke over here, it will become what? Put everything over here. It simply tell you x square psi dx plus psi star x square dx. Great. Okay, psi minus psi star to whatever you want to say, x hat and delta x. Okay, average of x, and this is psi dx, right? Yeah, very good. Now you see that psi star psi, it's kind of average. Therefore, I have written over here that it simply will give you an operator, and there is an average of this one. This is a number because it's already gone average. It's a number and will have psi star and psi. Psi star psi dx gives you the probability. Therefore, this is nothing but this guy over here. Again, here we have this one is simply average, some number. Psi star got x hat, this psi will give you the average of this guy, right? So now it becomes squared. This square minus this square will be x square minus x whole squared. Wait, that's why I call it the expectation value of the uncertainty, right? If you just give it the squared over here, you will get that the square. So now it has the definition of this uncertainty in the quantum sense. There I have defined a quantity. The quantity is delta x hat is the true value minus the average of this. Acting on this, it will give you the new state, but let's define that delta x square is your standard deviation. sigma x. So what is the value of, if I just take an average, because average is the important, then what is the value that I'm going to get? Sigma x square is x square minus x whole square, right? And similarly, I'm going to get, if I have the momentum, because it's not only the position change, also the momentum change, right? Because these are two things going one to by one. The position shift, momentum also shift. If I just see everything in terms of x, the corresponding momentum in x will also shift, right? So the problem is that you cannot simply say that if I'm throwing a light, I will just only know the information of x. This information you will have a degenerate effect. Degenerate means that it has the two information you are going to get, x and px. You are not allowed to just get one information. You are going to get one variable associated with another variable. But keeping that, okay, energy is not going to change. The third variable energy is keeping the same. But these two guy will going to change. So one of the key problem over here that in classical mechanics, we are easily see what is the position, and I can say that okay, this is the position, then I will infer that this is the momentum. So these are two quantities, they are related, but I can independently measure it. Over here, these quantity are related, and I am not going to independently measure them, because if I am measuring it, another thing is also associated with it, right? So it's kind of dual thing. For instance, what is, let's say if I'm defining that, let's say alpha is equal to E by P, anything E by P. If I know alpha 0.1, now E and P could be anything that can make 0.1. In some sense, they are paired quantity. They have now become a paired quantity. So I have to devise some other experiment to actually break the degeneracy. This is something called degenerate, because there are infinite values, infinite possibilities of E and P that will give you the same value 0.1. So outcome is known, but this individual quantity cannot be known. Therefore, we have to do some following different experiment to actually break these called these. We can simply say that these are degenerate parameters, right? These are paired parameters. Okay. So now we know what is the uncertainty in x. Similarly, I can define sigma p squared, and this simply become p squared then average, p average then squared. Now these are individual terms, right? Now we wish to calculate that, okay, as these are degenerate parameters, therefore there could be some cross term. Let's just calculate this cross term, sigma x square and let us say sigma p squared. What will happen? So let's calculate average of delta x and delta p. Delta x and delta p have the average. Delta x and delta p acting on the psi, because psi is the wave function we are talking about. This becomes psi star delta x operator delta p operator psi dx. Okay. Now you see, if I am writing it, x operator minus average, p operator minus delta p psi dx. Many times I am leaving hat and so on, so don't worry about that. Now I have to see that I'm going to, because these are the linear operators, therefore what I have to, just for a moment, do not try to pollute their orders. Okay. Right now, I'm not giving you any reason that, okay, why you should not, but when you are doing the mathematics, do not try to, give the order, because 2 into 3 is same as 3 into 2. Do not try to do this. Okay. Because for the real number, it is very good, but for a complex number, it's kind of very difficult. And you understand that these x and p's are the complex number, so it's kind of a bit problematic. Okay. X, P, X, P, and this is x and p acting on psi dx. Now we say simply psi star xp psi dx minus, it's just a number, psi star x psi dx. Again, this is going to be number, psi star p hat psi dx. These are just a number, I'm just writing it because again psi star psi will become 1. So why to worry? It should be plus. Thank you very much if you have pointed it out. And this guy, right? So if I do the calculation, you will see that I am going to get this average, writing this one as it is, xp. Do not try to, write it I h bar, so on and so forth. No need, no need. I will have delta p delta x minus x. These are numbers. Now you can change the order, whatever you want to do. You may do. I'm not going to stop you. Cancelled. I got, if I find the average of these quantities, this is the thing I'm going to get. Let's change the order, because if I just having the cross term, they will have this term and this term, right? A into B plus B into A, something like that. Therefore, I can write P delta x will have psi star, P will go over here, x will go over here, dx minus x, all the order will change, p x bar plus x bar p. Yeah, no problem. Wherever you want to write, just write them. Again, this guy will cancel to this one. Now you see that if I'm just taking a negative, this becomes positive. Px get cancel out this one. I'll get something interesting. I'll get xp acting on it, negative delta p. Come on. Delta p delta x will give you psi star xp minus px psi dx. So those who have already read quantum mechanics, they know that this is the commutation relation. But for a moment, I'm going to just tell you that, okay, whatever this is the negative, this is, I am denoting a thing called square bracket x comma p. We have already seen that if this thing happens in the Hamiltonian video, right? When we discuss the Hamiltonian video, let's say that you have to find out at some time derivative of any quantity, let's say q, generalized coordinate, then we have arrived at this kind of thing that can appear. I'm just simply say that whenever this quantity, let us say a quantity, b quantity, and reversing their order, they are not going to cancel out. Remember it, right? I'm going to just simply denote this guy dx, and since this is the averaging thing, averaging of this quantity, good, and this is equal to this and this. I know that my lectures are very lengthy, but and I'm not a very good entertainer, so you have to take a next level effort to actually stick with these lectures. Now once I do this thing, I know these are the expectation value, but the problem is that I have bunch of quantities. These bunch of quantities are like the expectation value of the standard deviation in x and p. I know what is the cross term, but you see that, and I also know that x and p are kind of intact. Therefore, what should I use? There is a called Schur's inequality. Schur's inequality. Let us say you have two vectors, and they say that you have two vectors. You are going to take a modulus, and then you are squaring it. You are going to get the product and then squared, right? So let us say you got a two vectors. These source inequality. The source inequality states that you got a two vectors. What you simply say about them is that the length, you just basically trying to say the length, because a dot b is again a scalar quantity, and this has to be scalar. This tells you the length of the vector, and you just take the dot product, and you will get that this length squared is always going to get greater than this one. Now, if let's say that A is the complex quantity, then how this game would play out? So A square would become A star A, B star B, right? And this guy would be like something called A star B. A star B, okay? So one of the complex conjugate and another thing, you can just keep it real. Now, if I'm translating things, let us say that I have two different wave functions. Let's say a and b represents two wave function. So it becomes, let us say, one is psi, another thing is phi. Okay, this should become like psi star phi, but I will say, I will just mark it this one. That's it, simply tell you. But when we are talking about it's the product psi star phi, right? It's a way of representation. Let me just write not anything. Now, one thing is I can simply do over here is the following, because we are dealing with the quantity called wave functions. I have to take an average. Average. I'll just use these notations. Average. Average. This basically tells you the average of these quantities, right? No difference, nothing. You have just like psi star psi dx, phi star phi dx, and mine is not going to be completely equal to 1, because psi is not a complete whole 1. Psi and phi are interrelated, so they have some different probabilities, just like a and b. And similarly I could write psi star phi and dx. These things I think you have to clear, right? Okay. Now, why we are writing source inequality? Because we are trying to measure this delta x and delta p's, right? So delta x and delta p, these are two operators acting on wave function psi, and since they are different, they are going to produce two different wave functions, two different states, right? Delta p psi, p on an average p psi could be like, no, I should not write this one, var phi, depending on the position state, right? So delta p also acting on psi, it triggers a different kind of state. Now you may say that where is the eigenvalue? Eigenvalue can be get lambda, but I told you that this has to be real, so I'm not actually talking about what would be the. So this is kind of an estimating that, okay, what would be the error in this if I just try to measure it. So now the absolute value is gone. I am just looking at this, the error, right? So phi and psi, right? So you see that if I have this thing phi and var phi, then I will translate it like, let's say that I have phi star phi, okay, if I'm doing right, psi star psi greater than, okay, phi star and then var phi. This is the inequality we have to invoke. Now you see that there are two cross terms. Well, we have something similar over here. Delta x, delta p, delta p, delta x, right over here. Correct? So let's say that, okay, phi is proportional to this one and psi is proportional to this one. Then I can have, I can, I can work it out. Wait a second. So there is a squared quantity. So over here I have to imply some squared, because this guy a star b star and this guy always have some squared, sorry about that, and this guy would also have some squared. So if I just do is, what I will get that, this phi is what, delta x will acting on psi. This phi star is what, again, delta x will have to act on psi star, right? And then I'm going to take an average. Wait a second. Then I will take an average like this. So you see that if you have anything like AB star, this becomes B star and A star. This is the complex conjugate phenomena. You can just simply invoke over here. You will get psi star. This delta x is Hermitian. We have already seen that it has to be Hermitian. Then it will give you the real quantity. This become delta x square and then psi. Similar thing I'm going to get over here. Uh, Psi star. This p, why I'm laughing? I'm laughing because you see that I have used something interesting. So it simply becomes the average of this guy, the average of this guy. Basically what it is, right? I'm taking the average and average, correct? But over here, it simply tells us that, okay, this is a still phi star and this is psi star. So what should I write? Again, I will do phi star, right? Phi star is x operating on delta x operating on psi squared. Again, phi is delta p operating on psi. Cool. So, but it has to be complex. No, why I'm writing this squared? Okay. So this is going to be, let's say, psi star, delta x star would be delta x, delta p, right? And this is psi square. It's basically averaging. So my, writing this would be a little bit fuzzy because I have already used the angular bracket. Therefore, you are seeing something, nasty thing. But basically, psi star, this whole quantity is psi is your average quantity. Therefore, this would become delta x, delta p, now becoming average, and then there is a squared. This is equal to delta x squared, delta p squared. These are the uncertainty in x, uncertainty in p, and this is equal to delta x, delta p. Now you have a cross term, delta x and delta p squared, but delta x and delta p is equal to this commutation. But the problem over here is that you see delta x, delta p, again we have delta p, delta x. This is we have to somehow resolve it, that okay, what will I get if I have this situation, right? So yeah, we have the solution. The solution is, let us say z is equal to a plus ib, and I got z star a minus ib, right? So if I just negative it, I will not have any real quantity. Real is not too much fascinating over here. I got 2ib. Therefore, b is 2i z minus z star, right? And let's say that if I try to find out the modulus, this becomes a square b square. I told you that the fascinating thing is that a square is not too much important. I'll simply say that z square is can be written as this b square. This z square is simply can be written as 1 by 2i z minus z star, then squared, right? You may say that is fine. Now let us say that this z is nothing but delta x delta p, and let's say that we are going to get squared whatever this guy. Then what will happen? I will get 2i, very good. Z is this guy, delta x delta p, this minus delta x delta p, then the conjugate of z, conjugate of this guy. So it's actually inside, yeah, because I told you that this is the expectation value I do, because z is kind of this guy squared. This is I, this is the complex conjugate, okay? I told you. So I to the power this one as a square would become I star and I. So minus I into I into I is minus 1, minus 1 has become plus. So it simply becomes plus delta xp and delta xp star, average delta x delta p. I told you they are going to switch the sign, switch the positions, delta p operator, delta x operator, then average, then squared, and I got something interesting. You see that 1 by 4, this guy has something, this guy has something, this guy has something. Okay, I got this one. This becomes average of this commutation relation, average of this square bracket. So this guy would become again average X operator, then P operator. Okay, then average, then squared. Very good. Now, I know this one. This one is greater. Oh, this one is greater. So this one is greater than this guy. Delta xp squared. So this equation is greater than this guy. This equation is also greater than and equal to this guy. What does it imply if you compare it? So this guy will become superior. Superior to what? This least one, isn't it? Because this guy is greater than this one. So let us say 2 is greater than 3 and 3 is greater than 1. No, sorry. 5 is greater than 2. 5 is greater than 2 and 3 is greater than 2. 5 is greater than 3. 3 is greater than 2. I can say 5 is greater than 2. Right. There is again an equality sign. I simply say that this guy that I have written over here, copy and going to paste over here. That, this guy, exactly this guy, wait a second, what I'm going to do. This guy is going to be 1 by 4th of this square, right? X and P square bracket and then squared. And it's nothing but delta x squared, something like that. Delta p squared 1 by 4th. Yeah, delta x squared, delta p squared. I must, what I have done. And delta x squared, we have already taken delta x squared. Delta x squared is what? This operator delta x squared is what? Delta x square, we have defined as sigma x square, right? Yeah, indeed. My notations were polluted like a quantum system. Okay, and this guy would become sigma x square, sigma p square is greater than 1 by 4. Take an average. I'm always, kind of very, very, very bad at writing these things because these are. And if I just remove this jumbo combo, operator, whatever, it is 2 xp. That's all. Oh my god. This was hell. Right. Now you see that, okay, what is this guy? X hat p hat minus p x hat. You just use this guy and you will see, because again in the end of this one I have to calculate this guy over here. So let me just start from this xp. Now I'm going to invoke x star p x hat I h bar del x, I h bar del x, x hat psi dx. So you see over here, psi is going to be over here, psi star, I has this gone. You go like this dx psi, correct? Dx minus I h bar psi star dx. It is going to act on x as well as psi, correct? Integral dx. Good. Now I h bar going to be common, psi star x hat dx psi dx negative of, this guy becomes psi star. Apply the chain rule. The chain rule stated is becomes dx psi. So dx going to be, because x hat can also be written as x, dx by dx is going to be 1, becomes psi, and then there is plus, I'll write psi star x d psi by dx, and then everything is going to be dx. Psi star psi is probability. Yeah, this has to be 1, right? And this guy minus and minus would be, this guy would cancel out. I got only I s bar, and this I s bar is proportional to what? This is equal to what? This is equal to this guy. So average of x hat p hat square bracket is going to give you, this is minus h, right? So this is going to be minus h bar. So if I just invoke over here minus h bar is going to be half expectation of any number, average of any number, okay, is not going to change anything. And I of this modulus would become what? I star I, not going to change, right? So, and h of this complex conjugate is just h bar. H bar I into I becomes positive of I, right? H bar by 2. So sigma x, sigma p operator, it simply tells you that, the error when you try to measure x as well as p will always be greater than h bar by 2 at minimum. That's why that we have to find out that, okay, what would be the minimum if I take the scale where the least count is starting from 0.1. It simply says that you cannot just measure with this device beyond 0.1, right? Similarly, over here, if I try to measure my position, I have to also measure, consequently I have to also measure the momentum, and these are kind of degenerate. But when we try to measure the x or try to find out the error, when you try to measure the x, there would be some happen with sigma p. The uncertain relation also can be written as delta x delta p is written than h by 2, right? So the error always be greater than h bar by 2. That is the minimum limit. It is not upper limit, it's the lower limit. You cannot go beyond this. You have a quantum system, and nature has put, the way you are interacting with the quantum system, nature has put a very interesting limit onto you that beyond this, you will not able to get anything. And there are let us interpretation that if you want to go beyond this one, then you will encounter some kind of a black hole, and the information cannot get out from this black hole, right? But I'm not going to that topic right now. But the thing is that if you want to measure, let's say that h bar by 2, and let me say there is uncertainty in p, okay, delta p is uncertainty in p. If I know that if I have a quantum particle and I exactly know what is the momentum, if you know exactly what is the momentum, uncertainty becomes too low, near to zero. If this quantity becomes too low, what happens to this position? It becomes extremely great. And this is the Heisenberg uncertainty principle. We have not derived from any experiment. We have just derived by using the Schrodinger equation, using the operators and wave functions. And this is true for anything. So you can just replace sigma x by sigma a b, and you will see that you have to obtain the commutation relation, this relation. So if you know what is your operator, you can easily get it the way I have done it over here. There is no any jumbo combo, right? So I know what is this square bracket will give me. The square bracket of x and p will give me minus of I h bar, right? Very interesting, isn't it? So you see that if I exactly know what is the momentum, the x would become infinitely large. If I know exactly the position, the momentum would be infinitely large. Therefore, let us say that if you want to try that, okay, this is the location of your electron. The moment you know the location of the electron, the momentum would be infinite. It becomes absurd, right? So that's why you see that when you try to take a measurement, we are not going to get the whole information. The uncertainty will be there, and h bar is the quantity, which is again 10 to minus 23. It's it's a comparable quantity when we try to talk about the quantum level. But when you come to the classical object, minus 23 feels nothing, right? So I hope this lecture gives you the glimpse that, okay, where we are going. We have not taken any feedback from the experiments. We have just uh, used our mathematical intuitions, mathematical framework, and derived everything systematically in such a way that you will not feel terrible that, okay, what the hell I am learning. So everything exactly makes sense. Superposition principle we have discussed initially, how the transition has taken place from classical superposition to quantum superposition. Then we have talked about that how the operator will play, and what should be the relation that an operator must follow. And then we hit that measurement problem that if you try to measure any quantum particle, then you have to talk about the error, and then error would become huge. The uncertainty becomes huge if you try to find out the accuracy. The more you will get accurate, the other variable would become less accurate, right? And this is the kind of thing that we are getting, not just only mathematically. It's verifiable, it's verified using a lot of experiments. So it's not just a mathematical jumbo combo, it's the real thing. It's the real thing we are talking about. So the kind of the nature has locked us that, you see, Baba, you are not going to get anything substantial if you try to unlock me quantum mechanically. Classically, you may say no, whatever you want to do anything, but quantum mechanically, I'm not going to reveal. You have to think of something to actually figure out, to actually know the mystery. And these are, I tell you that these are the most important thing that is going to play if you really want to solve the quantum gravity problem. All right. So we will be discussing that thing in detail maybe later on, maybe when we have finished all the quantum relativistic chapters, spin problem, and so on. But before that, I have not told you to subscribe my channel and like my video and try to share it, and do not download it. Okay, do not download, because this time if you're watching from India, it's like data is free. Do not try to download it. And if you have seen that, okay, my lectures has been copied and distributed and somebody is earning money, then you can just let me know, because these are I'm providing everything in free. But later on I will also write a book on it. You have to wait for it because I'm a little bit busy, but yeah, I will write a book on it, and you will enjoy the lectures, reading it, everything I will write there. So quantum mechanics from a scientific perspective, and it's for the people who transitioning from class 12 to this whole situation. All right, just like me. If you just want to teach me, like, okay, you have to just eat it, I'm not able to eat it. I require some transition, some smooth transition. I'm not a quantum particle, I don't like jumps, I like a smooth transition, right? So that's why I'm making this video, and I hope you like it. This is Dr. Saddam Cap signing out. Bye bye, take care.